Okay, so today we're going over multi-loops circuits and Kirchhoff's voltage and current laws. Now, we know that we have seen Kirchhoff's voltage law before. So we know that the algebraic sum of all the voltages around any closed loop must equal to 0. So, for example, what it means that if we have a series circuit where we only have one single loop in the circuit, right? And let's say that we have 3 resistors connected in series with the power supply. So this is my E. Let's say this is positive, and let's say this is R1, R2, and R3, and that the voltage drop across each resistor, this is V1, V2, and V3. It means that if we go around the loop and add all the voltages, it must add up to 0. So what it means that E minus V1 minus V2 minus V3 has to add up to 0. So this is the first law. This is called Kirchhoff's voltage law. Okay. Now, on the other hand, if we have a junction where a current is coming into a junction, let's say the junction looks like this, right? And if we have the current I is coming into the junction, and then when it gets to the junction, the current is going to split. Some of it going to go this way, and then some of it going to go that way. Let's say this is I1 and I2. So what it means that I, the current that's coming into the junction, minus I1 minus I2 has to equal to 0. So what it means that the total current into any junction is equal to 0. Kirchhoff's current law. As a result, we can also say this, that the current I is equals to I1 plus I2. So what it means that, again, the total current that is coming in or entering the junction has to equal to the total current leaving the junction. Okay, so again, this is Kirchhoff's current law. Okay, so what it means that the sum of the current entering a junction has to equal to the sum of the current leaving the junction. Okay, now again, this is another junction rule. So if we're looking at this current that's coming into this junction, I1, so when it gets here, it's going to split. If we label this one as I2 and label this one as I3, the current is going to split in this fashion. So we can assume that I1 is equals to I2 plus I3. Now, before we can solve any multi-loop circuits, we must apply Kirchhoff's current law and also Kirchhoff's voltage law. Now, before we do so, also we must also determine how current flows in a resistor. So if we have a resistor, if the flow of current is moving this way, right, current is always going to flow from the positive side to the negative side. And then this is how we can determine the polarity of the voltage across the resistor. And then if we're going from, for example, from plus to minus, right, from plus to minus, so usually that the value that we assign to the voltage becomes a negative voltage, right? Okay, and then let's say that we have a resistor and that current is flowing to the resistor in this fashion. So again, current always flows from positive to negative. So here, if we're going from negative to positive, if we're going from negative to positive, so the voltage across that resistor is going to be a plus voltage or plus value. Okay, and again, before we can solve multi-loop circuits, we have to satisfy the Kirchhoff's current law. Okay, so what it means that if we have a current that is coming into the junction, I, so when it gets to the junction, the current is going to split. Let's say this is I1 and this is I2. So I is going to equals to I1 plus I2, Kirchhoff's current law. And again, this is arbitrary. So it doesn't matter which direction we give the current, just as long that we satisfy Kirchhoff's current law. That is, the current that is coming into the junction is equals to the current leaving the junction. So let's say, for example, that the current that is coming into the junction is labeled here as I1. So what it means that if this is I2 when the current splits, and then this is I3 moving this way when the current, splits, right? So we can also assume that I1 is going to equals to I2 plus I3. So that is, the current that is coming into the junction is equals to the current that is leaving the junction. Again, so these two things, we must actually satisfy them, the way current behaves in a junction, and also how current flows in a resistor in order to assign the right polarity across the resistor. Now, here's an example. So for this example, we have the power supply E1 is 12 volts, so that's 12 volts. And then we have R1 is equals to 4 ohms, R2 is equals to 4 ohms, and R2 is equals to 2 ohms, and E2 is equals to 8 volts, right? Now again, as you can see, so one of the first thing we must do is to draw our currents for the junction rule. And the fact that is the current I1 is coming to the junction, you can see that I2 and I3 are leaving. So therefore we can say that I1 is equals to I2 plus I3. So we satisfy the Kirchhoff current rule. Now, and then also we must assign the polarity across the resistor, since now we know how current flows in each element. So from here, the resistor here, current flows from positive to negative, so this will be the right polarity of the resistor. So here will be plus, minus, and here will be plus, minus, right? Now, it doesn't matter how we add the voltages around the loop, we have to be consistent. We can go clockwise or counterclockwise. So for example, if we're looking at the voltage, if we're adding the voltage in this fashion in loop 1, right? And let's say, for example, we're starting on, let's say we're starting here with R2. So we're using Ohm's law. We know that V is equals to I times R. So if we want to find the voltage across R2, so it's going to be I2 times R2. So if we label that as loop number 1, so the voltage across I2, so it will be I2 times R2. And then since we're going from plus to minus, so it will be a negative value. So it's going to be a negative voltage to begin with. And then we adding plus E1, so that's the voltage is positive. And then we're subtracting voltage across R1, so that would be I1 times R1, and then that equals to 0. So again, what it means that if we're looking at the negative sign, if we're going from the negative sign to the positive side, what it means that we are going from low potential to high potential. That means that the potential is rising, right? And then if we're going from a negative potential to high potential, it's always going to be a positive value. And then on this case here, if we're going from a high potential, which is the plus sign, it means that it's high potential, to a low potential, it means that the voltage is falling, and then we assign a negative sign. So this is how it works. It's the inverse. So wherever you're starting with, it's always going to be the inverse of that sign. And then if we're looking at, and then we can rewrite this so that it actually looks better. So if we rewrite this, so we're going to have, we're going to have negative I1 times R1, right, minus I2 times R2, and then if we bring the potential across on the other side, so this becomes equals to negative E1. And then since they're all negative, right, since they're all negative, we can basically say that they're all positive by multiplying by a negative 1, right? So what we have is that I1 times R1 plus I2 times R2 is equals to E1, right? And then we can do the same thing for loop number 2. If we're starting on E2, for example, we're going from plus to minus. So again, so this will be minus E2, right? And then minus I3 times R3, and plus I2 times R2 is equal to 0, right? So now we can also rewrite this so that it looks a little bit better. So if we transpose this, so we're going to have I2 times R2 minus I3 times R3, right? And then this is going to equal to E2, right? Bring that on the other side, this becomes to E2, right? Now, what you have to see, right? So this is I3 times R3, and then this is E2, right? Now, what you have to see is that the variables are not the same. So we have I1 here, we have I2 here, and then we have I2 here and I3 here, right? Now, as you can see that the variables are not common, right? Now remember, for example, when we look at, a system of equations and unknowns, So for example, if we have 2x plus 3y is equals to 0, or I don't know, 3x minus y minus 1y is equals to 6. As you can see, the variables are exactly the same, x and y and y. Now if we look into these equations, they are not exactly the same. So the only one that's common is I2, right? We have I2 common in both, and then we have I1 and I3, they are not common. So but since we know that I1 is equals to I2 plus I3, we can substitute it into this equation so that we can make the second one look like the third one, like the first one. Okay. Now, so to do this, what we'll do, so we know that the equations were like this, right? So the first one, so we had I1 times R1 plus I2 times R2 is equals to E1, right? Now, in this case, if we substitute I1 for this one, so what we have, so I1 is equals to I2 plus I3. So if we multiply that by R1, and then plus I2 times R2, and then that equals to E1. And then if we multiply it, this becomes I2 times R1 plus I3 times R1 plus I2 times R2, and then that equals to E1. Okay. So so this is I3 times R1, right? Now we can see that these two terms are exactly the same. So we can combine these two terms. So what we have, this becomes I2 times R1 plus R2, right? And then this becomes plus I3 times R1 is equals to E1, right? Now, so we can substitute the values. So this will be 1. So 1, so this will be 8 times I2, right? Plus 4 times I3, right? 4 times I3 is equal to 12, right? And then our second equation was, and then remember that our second equation, right? If we look at our second equation, it was I2 times R2 minus I3 times R3 is equals to E2, right? I2 times R2, it was I2 times R2, right? Minus I3 times R3, and then that was equals to 8 volts or E2, right? So if we substitute for R2, so this will be 4. So this will be 4 times I2, right? Minus 2 times I3, and then that equals to, 8 volts, right? That equals to 8 volts. Okay. Now, so now we have two equations and two unknowns, and as you can see, we have I2 and I2 is the same, I3 and I3 is the same, the variables are exactly the same. So now if we multiply this one, right, by 2, right, and then what we get, so this becomes 8 times I2 minus 4 times I3 is equals to 16. And then if we add these two equations, what we have, this will become 16 times I2. So we have 4 I3 minus 4 I3, that goes out to 0, right? That goes out to 0. And then that comes out to be equals to 16 plus 12 to equals to 28. Okay, so therefore what we have is that I2 is going to equals to 28 divided by 16 to give me 1.75 amps. Now, if we go back into one of the equations, right? Let's say we go back to this one, right? And then we plug in for I2, we should be able to solve for I3. So what we have, this will becomes 8 times 1.75 plus 4 times I3, right, is equals to 12. Okay. Now 8 times 1.75 will give me 14, so we have 14, right? Plus 4 times I3 is equals to 12. Bring that on the other side, becomes minus 14. So what we have is that 4I3 is equals to minus 3. And therefore, if I solve for I3, so I3 is going to equals to minus 2 divided by 4 to give me minus 0.5 amps. Okay. Come on. Now, so now that I have I2 and I3, now remember that now I1 is equals to what? I2 plus I3. So if we're looking over here, I1 is equals to I2 plus I3. So remember that I1 is equals to I2 plus I3. Right? So now we have I2 and I3. So this becomes 1.75 amps plus a minus 0.5 amps, right? And then what I'm left with is that this comes out to be 1.25 amps. Okay, so this is my I1, right? Now here for I3, the negative sign, all it means that, you know, the direction that we chose for I3 is the inverse direction, is the opposite direction. So that's all it means, that the current is moving in the opposite direction. That's all the negative sign means. Okay, now this is how we can actually use Kirchhoff's current law and Kirchhoff's voltage law to determine the unknowns, and then in this case the current that is flowing into the circuit, I1, I2, and I3. Okay, now for this example, giving the following circuit, you know, and then we are going to be using both Kirchhoff's voltage and current law to solve for I1, I2, and I3. And then as you can see that I already gave you the current direction, and then from that you can determine the polarity of the voltage across each resistor. So we know current flows from positive to negative, right? Current always flows from positive side of the resistor to the negative. Same thing over here, plus to minus. Now and look at the power supplies, the voltage source. There's nothing that we can do about the polarities. They are set, we cannot change them. Okay, so they stay the same. Now again, if we look at the current, here we have I1, right? I1 is coming to this branch and I2 is coming to this one. So we can see that by Kirchhoff's current law, so I1 plus I2 is equal to I3. Okay, so that's Kirchhoff's current law first. We determine that. Okay, now if we go around the loop and add all the voltages, so let's say we go around the loop, for example, and add all the voltages around the loop, right? And then it doesn't matter if we go clockwise or counterclockwise, but we have to be consistent in every loop, right? So we have to be consistent. So if we call this loop number 1 and loop number 2, so here we're starting at the negative potential. We're going from low to potential to high potential. So we know this is going to be I1 times, it's going to be 4 times I1, right? It's going to be 4 times I1. So the voltage across the 4 ohms, right? So this will be 4 times I1, and then here the voltage will be plus 12 volts, right? And then minus 3 times I2, right? And minus 6 is equal to 0. Now we can rewrite this and transpose this. So this will be 4 times I1 minus 3 times I2. So we have 12 minus 6 will give me 6. Break that on the other side, becomes a negative 6. Right? So we have 4I1 minus 3I2 is equal to negative 6. And then again, if we're starting over here for loop number 2, so let's call this one 1, right? So for loop number 2, so what we have, if we're starting over here, for example, well, let's say we're starting over here, right, at the 3 ohms, so this becomes 3 times I2, 3 times I2 minus 12 plus 6 times I3, right, and then plus 20 is equal to 0, right? And then again we can rewrite this, so this will becomes 3I2, and then we have plus 6I3 plus 6I3, and minus 12 plus 20 will give me 8. 8, bring that on the other side, becomes negative 8. Okay, So now these are the equations that we have, right? Now look at our variables again. We have I1 here and I2 over here. We have I2 and I3 here. But remember that since I2 and I2 is coming in both, so we want to keep those two terms. And then since we know that I3 is equals to I1 plus I2, maybe we'll substitute for I3 over here and solve, and then so that we can make equation 1 looks like equation number 2, so we can solve for either I1, I2, and I3. Now, if we go on the other side, right? So what we are going to have, so we have, first we have 4I1, right? 4I1 minus 3 times I2 is equals to -6, right? And then for the other one is that we have 3I2 plus 6I3 is equals to -8. 3I2 plus 6I3 is equals to -8, right? So, and then we know that I3 is equals to I1 plus I2, so we can substitute for I3. So now let's say that we substitute for I3 into this one, so we're going to have 3 times I2 over here, right? Plus 6 times I3, so that would be I1 plus I2, and then this equals to -8. And then what we'll get, so this becomes 3I2, right, plus 6I1, right, plus 6I2, right, and then this equals to -8. And then we can combine these two terms, right? Combine these two terms. So what we have is that 6I1 plus 9I2 is equals to -8. Now we have these two equations exactly the same. So now we can combine these two equations. 4 times I1, right? Equation number 1, that's number 1, right? And that was number 2. So now we make number 2 looks like number 1. So 4 times I1 minus 3 times I2 is equals to -6. And then we have 6 times I1 plus 9 times I2 is equals to -8, right? So now if we multiply this by 3, if we multiply the top equation by 3, right? So we can actually if we multiply it by 3 all the way, right? Multiply everything by 3, right? So we can actually use the process of elimination. So this becomes 12 times I1, right? Minus 9 times I2, and then this equals to minus 18. And then by adding these two equations, right? By adding these two equations, so what we have, this becomes 18I1, right? And then this cancels out, and that equals to minus 26. So if we solve for I1, so I1 is equals to minus 26 divided by 18, and what we get is negative 1.44 amps. Okay, negative 1.44 amps. Now, if we take that negative 1.44 amps and then we go to one of the original equations, we should be able to solve for I2. So, for example, we have 4 times I1, so that would be 4 times negative 1.44, right? And then minus 3 times I2 is equals to minus 6. So 4 times negative 1.44 will give me 4 times 1.44 give me 5.76. Okay, so so I have 5.76 minus 5.76 minus 3I2 is equals to negative 6, and then bring that on the other side. So this comes out to be 3I2 minus 3I2 is equals to minus 0.24. Okay, so bring that on the other side, becomes a plus 5.76 minus 6 will give me minus 0.24. So therefore, if I solve for I2, so I2 comes out to be pretty much 0.08 amps. Okay. Now that we know I1 and I2, we can solve for I3, right? And then we remember that we know that if we go back, I3 is equals to what? I1 plus I2. So we know that I3 is equals to I1 plus I2, right? So what it is, so this will be I1 would be negative 1.44 plus 0.08 to give me that I3 is equals to simply 1.36 amps. Okay. Now, well, negative 1.36 amps, right? And then again, the negative sign just implies that the direction that we chose for the current to begin with is just that is the inverse direction. That the current is flowing in the inverse direction. That's all it means. Now, here's a circuit. Now, if we're looking at this circuit, again, we have in this circuit we have the 6 ohm resistor is consuming energy at a rate of 24 joules per second when the current through it flows in this fashion. Okay, so if we're looking at this 6 ohms here, so the 6 ohms that it's this 6 ohm, so we already know how the current is flowing through there. Now remember that power, right? Power, the units for power is watts. And what is watts? Watts is joules per second, right? Now, so we know that power, right? So here, so if we know the power across the 6 ohms, so the power across the 6 ohm is equals to 24 watts. So that is equals to 24 watts. That's the power across the 6 ohms, right? To the 6 ohms. Now, so what do we know about power? We know that power, P is equals to what? I squared times R, right? And then we also know that power is equals to I times V, but since we don't know the voltage, but we know the current and the resistance, so we can solve for I. So if we solve for I, so I is going to equals to P over R, right? And then take the square root of that. So it's going to be 24. So I is going to equals to 24, right? Divided by 6, and then takes the square root of that to give me the power. And then if we look for that, so the power across that resistor, okay, is going to the current is going to be 2 amps. Okay. So this comes out to be 2 amps. Okay. So what it means that the current that is in this branch, so we have 2 amps here, and we also have 2 amps here. It's the same branch, it's the same current, right? Now, now for this, we're trying to determine, okay, so what is the voltage, what is the current through the ammeter, and also what is the voltage through the 20 ohm resistor, and also what is the value of the voltage across the battery. Okay. Now, so one of the things that we must do here is actually draw our current, right? Let's say if the current is coming to this junction here, right, it's 2 amps. So some of its split goes this way and some of it goes that way. If we label this one as I1, if we label this one as I2, so all it means that I1 plus I2 must equals to 2 amps. Right? Now, now we have to add all the voltages around the loops, right? If we go around the loop this way, so we can add the voltages and satisfy Kirchhoff's voltage law for loop 1. And then we can do exactly the same thing here. And if we go around the loop here, right, and then add all the voltages. So what we have here, okay, if we're starting over here with the potential here, right, from the minus sign, so what we have, this is going to be E, right, E. minus, and then the way current flows. So here, current is flowing this way, so this will be minus to plus, right? Minus to plus, right? And here this will be plus to minus, right? This will be plus to minus, and then here the current is flowing this way here, right? So this will be plus to minus, right? And then here this will be plus to minus because current is flowing this way, and current is flowing this way. That will be plus to minus in this resistor. Now if we're looking at this, so we have E, right, plus 17 times I2, right? 17 times I2, right? And then plus 6 times 2 is 6 times 2 is 12, so that would be plus 12 volts, right? Plus 12, right? Minus 25, right? And then here, and then we have 2 amps and then 3 ohms, so V is equals to I times R, so 2 times 3 will give me 6, so that's going to be plus 6 volts, right? Plus 6 volts. And then here, this will be plus 13 times I2, right? Plus 13 times I2 is equals to 0. Now, so that's one thing. Now, and then for the other loop, what we have, so let's try to, for the other one, we can do exactly the same thing. So if we're starting here, so this will be, say, plus 25, minus 12, minus 12, and then here we have to take the equivalent resistance. So we have 20 in parallel with 20, so it's the product over the sum, and we know this is going to be 10, so this is going to be 10 times I1, so that's going to be minus 10 I1, minus 10 times I1, right? Minus 19 times I1, right? Minus 19 times I1, and then minus 1 times I1, minus I1, right? 1 times I1, right? And then minus 8. 3 times 2 is 6. 3 times 2 is 6, so it's minus 6 is equals to 0, right? Now, if we solve for I1, we should be able to determine what is the current through the ammeter, because the current that's passing through the ammeter here is basically I1. That's the current, I1, right? So here, so we have 25 minus 12, 25 minus 12, so and then minus 6, right? So 25, so minus 12 minus 6 will give me 18. So 25 minus 18 will give me 7. Okay, will give me 7, right? So, and then we have 10 I1 minus 10 I1 minus 19 I1 minus I1, so that will give me 30. So minus 30 I1, right, is equals to 0. So if we solve for I1, so what I'll get is that I1 is going to equal to 7 divided by 30. Okay, so in this case, my current for I1 comes out to be 0.233, right, amps. 0.23 amps. And then what it means that if I know the current I1, right, and then I know that I1 plus I2 is equals to 2 amps, so I can solve for I2. So if I solve for I2, so I2 is going to equal to 2 amps minus I1. So in this case, I2 is going to equals to 2 amps minus I1. So I2 is going to equals to 2 amps minus minus 0.2333. So what I get for I2, so I2 comes out to be 1.77 amps. I2 comes out to be 1.77 amps, right? Now that I have I2 1.77 amps, I can substitute it here into this formula, right, this equation, and solve for E, and then that can give me the potential across the power supply. Okay. So in order to do that, we can try to so let's try to transpose that on the other side. So we have E plus 17 times I2 plus 12, right? Go back, plus 12, minus 25 plus 6, minus 25 plus 6, right? Go back. So minus 25 plus 6 and plus 13 I2 is equal to 0. Plus 13 I2 is equal to 0. Right? So in this case, E, so this is going to equals to bring everything on the other side. That's going to equals to minus 17 times 1.77, right? Plus 12 minus 25 plus 6. Actually, no. This will be minus, so right, we're bringing everything on the other side, so this will be minus, this will be plus, this will be minus 6, and minus 13 times 1.77, and that will give me, and that equals to the potential. So now if I multiply everything out, and then what I come up with is that E comes out to be negative 46 volts. Right? So all it means that the polarity is actually inverse, you know, if we have a negative value. So we have, you know, so it's negative 17 times 1.7, bring positive 12 on the other side becomes a minus 12, bring negative 25 on the other side becomes plus 25, a positive 6 on the other side becomes a negative 6, and a positive 13 I2 on the other side becomes a negative 13 times 1.77. So we get E is equals to 46. Now, so we want to determine what is the voltage through the 20 ohms resistor, right? Now, when the voltage comes here, we know it's going to split. Somehow we're going to go this way and somehow we're going to go that way. And since the two resistors are exactly the same, it's going to be half and half. So we have, what's the current coming through here? It's 0.233 amps. So divide that by 2. If you divide that by 2, so that will give you the voltage, the current that's passing through each resistor, because since the resistor is exactly the same. So that's one way to do it. So to find the voltage across the resistor, V across the 20 ohms, right, is going to equals to 0.233 divided by 2 times 20, right, times 20, to give me a voltage of 2.33 volts. Right? Now, the other way we can solve this, the voltage, is that if we look at these two resistors in parallel, right, if they are in parallel, if we get the equivalent resistance, so we get the product over the sum, right, and then since they are exactly the same, we know that the equivalent resistance is going to be 10 ohms, and then 10 ohms, and then the total current that's passing through it is 0.233. So therefore, we can also determine the voltage across the 20 ohms, right? V20 is the equivalent resistance, which is 10 ohms, times the current flowing through the total current, which is 0.233, to give us 2.33 volts. We get the same thing. Now, so this is how we can apply, you know, Kirchhoff's voltage law and current law to solve for this type of circuit when we have a multi-loop circuit, and also understanding how current flows through the circuit, that when current flows through the resistor, it always flows from the positive side to the negative side, right? And then the fact that what we know about power, since we know that the 6 ohm resistor was consuming power at a rate of 24 joules per second, and then since we know that joules per second is watts, so power is equals to 24 watts. And then since we know that the power across the resistor P is equals to I squared times R, and therefore we can solve for I, where I is equals to the square root of P over R, and then we got 2 amps from there. We determine the circuit. Now, so to conclude this, now if we're looking at this circuit, right? Now we're trying to find which equation below is the correct equation for loop number 1. Now again, it doesn't matter how we go around the loop, right? Now let's look at the flow of current. So here we have I3s coming to the loop, and it's going to split. So we have I1 going this way and I2 going this way. So we know that the polarities will be plus to minus this way, and this one will be plus to minus. And then the voltages, we cannot do anything. And then the longest side of the battery is always going to be the positive, and this is always to be, the short side is always going to be the negative side. Okay. Now, so for loop 1, right? If we're starting the loop here and go around the loop this way, right? And let's say that, so what we have is that V2, right? V2 plus I2 times R2, right? And minus I1 times R1 is equals to 0. Okay. Now, so we're gonna see which one actually corresponds to that. So we can rewrite this. And then if we go the other way, right? So everything becomes the opposite. So this becomes minus V2 minus I2 times R2, and then plus I1 times R1 is equals to 0, right? So we have minus V2 minus I1 plus I2. No, so we have minus V2 plus I1 times I1 minus I2 times I2. So therefore this corresponds to this one, right? Right. So if we write this, so this will be the same thing, minus V2 plus I1 times R1 minus I2 times R2 is equals to 0. Okay, so it's the same thing. And then this and this are exactly the same thing. It's just that it's just the way you go around the loop when you add all the voltages. So depending if you go clockwise or counterclockwise, and then they differ by either negative signs. Yep. Now, for this one, again, if we use the Kirchhoff laws, which of the following statement is the correct one? Again, if you're looking at point B, so we have the currents that are coming in. So we have I3s coming in, right? So we have I3s coming in, I2 is leaving, and I1 is leaving. So we can say that I3 is going to equals to I1 plus I2. So the correct one would be this one, right? So we have I3s coming in, this is I3, right? And then we have I2 is leaving, and we have I1 is also leaving. Okay. Again, if we're looking at this one, which of the following equation gives the correct Kirchhoff's rules starting at point B and proceeding clockwise through batteries E and 2? Now, if we're starting at point B, right, and then we're going clockwise like this, clockwise, and then again we know how current flows, so this will be from positive side to the negative side. This will be plus, minus, okay, and current is flowing this way, going down, so that'll be plus to minus, and then this will be minus plus across this E3, right? Well, as a matter of fact, we're looking for E2. I think we're looking for E1 to E2, so we're not doing E3. So, and then if we're doing this loop for loop number 1, right? So this will be plus, minus, and then this will be minus plus because current flows from positive to negative. Right? So starting at E1, going clockwise to E2, So here we have I1 times R1, so that's negative because we're going from plus to negative. So we're going from low to high, from low potential to high, so that would be plus E1, right? And then from high to low, so that would be minus E2 and plus I2 times R2 is equals to 0, right? So minus I1, right, times R1 plus E1 minus E2 plus I2 times R2 is equals to 0. So it will be this one, number 5. That's the correct answer. Well, I'm going to stop here for today. And then what I'm going to recommend, and then I'll cover this in class, is to be able to do this example for homework, right? So do this example for homework, and let's see what we get. So you need to determine what is the unknown value of that resistor here, and also what is the current flowing through the ammeter too. All right. So this will be it for today, and see you next time.